This video is for section 6-7, quadratic functions and word problems. Here's an example. Each cable supporting the main span of the Golden Gate Bridge forms the graph of a quadratic function. The supporting towers are 500 feet above the midpoint of the cable and are 4,200 feet apart. Determine an equation for the curve described by the supporting cable. So here you have a photograph of the Golden Gate Bridge in San Francisco. And you can see that when you look at the shape, that it is a parabola. We're asked to find the equation of this parabola. If the parabola was superimposed on an axis system, where the vertical axis is this support column, and the horizontal axis runs along the roadway. Notice that that drooping cable touches the horizontal axis, and it intersects that axis 2,100 feet from the origin point. On a coordinate plane, that minimum dot, the vertex, would be the ordered pair 2,100, 0. There are two other points that we can easily identify on the parabola. The point right here where the parabola touches the vertical axis is 0, 500. And this point over here is 4,200, 500. From these known points on a parabola, let's make the equation. Let's start with the vertex form that we learned about. And let's fill in the values of h and k. Because the value of k is 0, you really don't have to write the plus 0 on the end at all. Next, let's use one of the other points that we know are on the parabola and therefore are solutions of the equation and substitute the values for x and y. I'm going to choose the y-intercept as the point. So for the value of y, fill in 500. For the value of x, fill in the 0. Now let's solve this to figure out the value of a. 0 subtract 2,100 is negative 2,100, which can be squared to make 4,410,000. Then divide by that number to get the letter a alone. A is approximately 0.0001337. Now that we know the value of a, we can go back and rewrite our equation in vertex form, using that number in place of the letter a. This equation models the parabola that the engineers of the Golden Gate Bridge used when they designed that bridge. Let's try one more example. A helicopter shuttle service operating between the airport and a nearby tourist spot charges a fare of $10 and carries 300 people every day. The manager estimates she will lose 15 passengers if she increases the price $1. Find the most profitable fare to charge. So the manager of this company needs to make a business decision. Is $10 the most appropriate price to charge in order to maximize the profits for the business? Should the business charge less, or should the business charge more than $10? To help us answer this question, let's fill out this table. If the manager makes no price hikes, that is, no price changes, then the amount of fare stays as $10, and we're told they have about 300 passengers a day. $10 per person times 300 people is a revenue of $3,000. If the manager raises the price of the fare, will that raise the revenue if they expect to lose passengers with the increased price? Let's investigate some different price hikes to see if there's a pattern. If the price is raised by $1, then the amount of fare is 10 plus 1, or $11. But we're told that they will lose 15 passengers, and they can expect to have only 285 passengers per day. $11 times 285 is $3,135. That is an increase in revenue. So it would be a wise business choice to raise the fare to $11. What if they raised it by $2? Then the amount of the fare is 10 plus 2, which is $12. However, they're going to lose 2 times 15, or 30 passengers per day, so that they can expect only 270 people to ride the helicopter. What's their revenue now? 12 times 270 is $3,240. Again, this is an increase in revenue. It would be a good business decision to change the price to $12. About $13. They project that if the price was $13, that they would lose 3 times 15, or 45 passengers. Then they could expect only 255 people to ride the helicopter every day. 13 times 255 makes $3,315. Again, an increase in revenue. So as the price of each ticket is increased, even with fewer passengers, the company is making more revenue. But this isn't going to go on forever, because at some point the price will be so high that hardly any people will ride the helicopter service, and they will have less revenue. Let's use algebra to find where the maximum revenue is. Let's look for the pattern in the rows. For the amount of fare, it looks like we're beginning with $10 and then adding the number of price hikes. In this row, adding 1. In this row, adding 2. In this row, adding 3. So if we use the variable x to be an unknown number of price hikes, we could have the expression 10 plus x. In the column for passengers, it looks like we're starting with 300 and then subtracting the number of price hikes times 15. That could be modeled as x times 15, or perhaps better, 15x. To calculate the revenue, we're taking the amount of fare and multiplying by the number of passengers. That is the expression 10 plus x times 300 minus 15x. And what we're interested in is, when is this expression a maximum? If you multiply this binomial times this binomial, do you recognize that you get a quadratic equation? If revenue is equal to 10 plus x times 300 minus 15x, then we could rewrite this as 10 times 300 is 3,000. 10 times negative 15x is negative 150x. X times 300 is positive 300x. And x times negative 15 is negative 15x squared. Most of us are more comfortable when the x squared term is written first, so let's rearrange the order of our equation. When rewriting that, I also combined the x terms together. We know from our recent lessons that the graph of this is a parabola, and because the value of a is negative, this parabola has a maximum. The maximum is located at the vertex, and the vertex is on the axis of symmetry. Furthermore, we know that the equation of the axis of symmetry is x equals negative b divided by 2a. In our equation, b is 150, so negative b is negative 150. In our equation, a is negative 15, so 2 times a is negative 30. This reduces to 5. The equation of the axis of symmetry is x equals 5. Because the vertex is on the axis of symmetry, the x-coordinate of the vertex is 5. And remember what the letter x represented in this problem. It was the number of price hikes from the starting fare of $10. So the best price for the company to charge is 10 plus 5, $15. That will maximize the company's profits. This application was a good one to study because it shows the kind of decisions that managers of companies need to make and how they use algebra to make those decisions. In this lesson, we worked two application problems together that, when modeled with algebra, created quadratic equations. We were able to answer the questions in these problems by using our algebra skills with quadratic equations.